in private meetings, but I'll go over our products and what we offer, and then kind of get into the technical presentation. I'll keep the company intro pretty short here, so don't worry about that. So Omnidots, we're based in the Netherlands, a Dutch company. Been around for about 10 years now, and one of the top monitoring suppliers in Europe currently. Right now we have two primary products, our vibration monitor, the swarm vibration. That monitor you see here is this same device here. That's an all-inclusive vibration monitor. So that's triaxial, we use MEMS accelerometers. That's got a built-in cell modem, some cool features like auto leveling and GPS for locating the device. And we also have a sound level meter. This is a pretty new product for us, so that just came out this spring. And that's a class 1 sound level meter, also using MEMS. The company's background is really in MEMS technology and different applications there. So, but this has all the same features. It's weatherproof. It's got cell modem. Both devices have Wi-Fi as well for communication. And really what the company's kind of approach to monitoring is we're trying to add value through efficiency to your projects. We do this through a number of aspects of the construction project. So starting off with a low barrier of entry. Part of that is price. You know, we don't want to be overpriced for the market. So we have a really affordable price point, a lot of that coming from that MEMS technology. And also by reducing complexity. So, you know, there's a lot of companies out there that get asked about vibration monitoring, but think it's this big, complex field that needs a lot of specialty. But we're trying to make that entry point a lot lower so that companies can really get in and start monitoring right away. Our monitors work in more applications. So as I mentioned, they all have a built-in cell modem. They also have built-in Wi-Fi. So flexible connectivity, and we have Ethernet connectivity. So pretty much any way you can get connection to this job site, you can get these things sending data out. That also comes from power as well. So AC power, battery power. This is our battery pack. Solar and Ethernet. We provide solutions for all of those basically out of the box. The monitors are super easy to deploy with one person. So with a lot of traditional monitoring systems, you're carrying around 70-pound car batteries to get these things to run for 2 or 3 weeks. And nobody wants to do that. So our system runs 1 to 2 months on this small battery you see here. I mentioned before, reducing that upfront cost of hardware. But there's also a big time component. So a lot of those hidden costs of reporting time, equipment setup time, calibration time, we've reduced all of those significantly with our product as well. So happy to provide more details and questions if you're interested. All of this kind of allows you to do more with fewer resources. And especially now, in the market with a lot of turnover and a lot of technicians moving here and there and engineers changing firms and things. It's a really critical time to have a really easy to use system so that you're not relying on one expert who knows how to make the system work. The system just works on its own. So one example of this easy to use system is our reporting tools. So a feature that we added over the last year is the ability to comment on the data. So here's an example of a vibration histogram report showing kind of background data and some events occurring during a plate compactor. And what you can do is you can add comments directly to that data set. So you can comment and say, hey, this is a plate compactor. You can put the comment in saying, I was on site during this time. I left site during this time. So you have all your field notes tied right in. And then when you export this as a report, it includes those comments in list form. They're all identified, chronologically. And that process can then also be automated for daily and weekly summary reports. So When you get a weekly summary report and you're used to spending an hour or two in Excel to create that every week, and then you have 10 projects, all of a sudden you're at a half full-time employee just to create those weekly reports, whereas we automate that and it takes no effort. So that's kind of it for the pitch with the company. I'll get into kind of the more technical things now. I wanted to just start out, in case anybody's not familiar with what vibration monitoring is. Basically, what we're talking about here is construction vibrations, so vibrations produced by heavy equipment on a job site. Those transmit into the surrounding buildings, or receptors, vibration receptors, what they might be. And they can cause damage, they can cause disruption, and a lot of complaints. And what this boils down to really is liability for the construction team. That they're trying to reduce liability by monitoring vibrations, because the reality is vibration damage is very rare and complaints are very common. So why do we monitor? Kind of the first reason, and kind of what drives everything in these industries, is a financial component. There's a value here for risk reduction in providing that early warning for vibration damage. Vibration monitoring is one of the few monitoring systems where we're actually trying to predict before damage happens. So before anything moves, before, a lot of instrumentation is monitoring when something starts to move. And we're trying to predict before that movement even starts. And so it's an early warning system that's fairly cost effective and easy to deploy. It also provides then a data record in case a claim does come up to show, this is what happened on our job site. We didn't exceed the thresholds. Everybody's okay. So kind of quells a lot of those complaints and concerns. The second component is the human component. And I'm going to talk a little bit about this environmental capacity here, which is basically what is the project surroundings tolerance for change? And environmental capacity is a very important concept for complaint management and perception of projects, where with vibration monitoring, this is typically one of the very first things that's happening on a job site, because you're digging in the dirt first. And so when you have these monitors on site and you're talking to the neighbors to get them deployed, you're able to show, hey, we're monitoring this proactively. We are looking out for you guys, and you don't need to worry about this. And that builds trust throughout the entire construction process. So there's a real opportunity here for kind of adding value to the project in that human component as well. Overall, it saves time because you're not dealing with as many complaints. Reduces the stress of your staff, so hopefully less turnover, and it has the opportunity to prevent legal costs as well. What is vibration damage actually? So for the vast majority of vibration monitoring projects, we're looking at things like on the left side of the screen here, with these hairline cracks off the corners of doors and windows. These cracks are basically in every structure already, and a lot of people are just not aware of them. So, part of the vibration monitoring process is often pre-construction surveys, where you're going in and documenting a structure and looking and showing that these things exist before the project starts. But this is also where most of the complaints come from, because vibrations happen, people start looking, they see these little cracks show up, whether they're new or not, and they think their house is going to fall down. But what today we're going to be talking about is the big stuff. So we're going to be talking about these settlement cracks, up to a couple inches of settlement, which is a real concern and often overlooked by the industry and a lot of the recommendations that are out there. There's a couple different types of vibrations. So the two primary types are transient. That's going to be like an impact type vibration. Think, demolition, where you're smashing a wrecking ball or ramming a bucket into the ground. You get that single impact and the energy dissipates, and you go on with your day. The other type is continuous. So that's what we see in the lower right here. Continuous monitoring or continuous vibrations are going to be longer term vibrations, and these have more of a potential for resonance. So they can kind of build energy within a structure or a receptor and cause more damage even than what you might be monitoring in the ground. The continuous vibrations are, again, what we're more looking at today, because that's the sort of thing that is going to cause soil movements as well. You can see soil movement from repeat transient vibrations. So if you have hammer pile driving and they're driving all day and banging in the same spot, that is also a result of, or can cause soil settlement. So something to keep in mind. But some of the research says that the potential is less with those instances. So primary concern is these continuous vibrations. Vibration thresholds. So there's a ton of vibration thresholds out there. There's a ton of research on this topic, but unfortunately there's no consensus. So there's not a national standard at this point. It's something that we could really greatly benefit from. And a lot of what's out there is especially in North America, is incomplete and contradictory, unfortunately. So I'm not going to dive into that today because that's a whole presentation in itself. But I wanted to give you some idea of what basic levels are for vibrations, just so you have some concept as I'm talking through some things later. So 0.01 to 0.05, that's kind of first perception for vibration, where you're going to be aware that there is a vibration, but you're not really going to think anything more of it. So think when your air conditioner is buzzing or something like that. A 0.1, that's where structures that are the most sensitive can be affected. Think museums, historic buildings with architectural finishes that might be extra sensitive. Buildings that are not in the best condition often get a 0.1. But really what a 0.1 is the vibrations of daily use. So that's going to be footfall. That's going to be doors closing at a normal level. You'll notice in a lot of museums that they have soft closed doors, because a door slamming can get you up closer to like a 2 inch per second range at times. A 0.2, so that's going to be kind of first potential for damage with continuous vibrations. That's a level that's annoying. If you were sitting in a room and a 0.2 is happening, you'd be like, man, I don't want to work here all day. This is annoying, but I'll finish what I'm doing. When you get up to a 0.5, that's our first potential with transient. And a 0.5 is going to be a strong vibration, where if you felt that, you'd go, oh man, this is strong. What's going on? Then when you get up to the 2.0 range, that's the level of first masonry damage. And that is a level that's intolerable. You would, if you felt a 2.0 in your house, you would leave the house because you'd be worried about it. What's important to note here, though, is these thresholds, which are kind of defined by the literature, are for vibrations to the structure itself. So this is only vibrations in the structure and not vibrations of the soils. And a common theme with a lot of these vibration thresholds is that they specifically don't account for vibration settlement. So Caltrans has a great guidance manual, transportation and construction guidance manual. Tons of good information about vibration monitoring in there. They say assessment of effects related to vibration-related soil settlement is beyond the scope of this manual. It's like 90 pages long, and they don't even touch on soil settlement. They do mention typically further than a pile's length is safe. So whatever that means. FTA has a 250-page transit noise and vibration impact assessment manual, no discussion of soil settlement. USBM, US Bureau of Mines, is kind of the gold standard for vibration monitoring research in the US. No discussion of soil settlement. Swiss standard is another one we often see. Soil conditions are not handled explicitly in the standard. So it's a common theme here that they acknowledge that there's something here, but they're not even looking into it, which is crazy because it's where the damage actually happens. Today we're going to be looking at two different approaches for how to handle the soil settlement. One is kind of a simplified approach, and this is by the German DIN standard, 4150-3. And the second one is a little bit more complicated with site-specific approach of some compiled research and a specific research paper that kind of helped as a source there. So DIN 4150-3, really catchy name. Vibrations in Buildings, Part 3, Effects on Structures, is put together by the German Institute of Standardization. And this is a really good paper. The challenge with it has been that it's not been readily available in English until recently. So in my time, I previously worked at Brown Intertech. In my time there, I kept trying to find this paper and could not. And just before this presentation, I looked it up and finally found it and was like, yes. So now you can search and you can find it on the internet. But basically, they have a soil settlement, which is a separate calculation from their general recommended standards. In this calculation, they have a non-cohesive soils one and one for non-cohesive soils where the pile tip is below the water table. So very simple approach here. Basically, what you're going to be looking at is if there's not a water table and you have non-cohesive soils, use a 30-degree angle from the tip of the pile to the base of the foundation, and that's your safe working distance. And if you have a water table, you use a 45-degree angle from the surface of the water table. So pretty simple approach, pretty basic, but misses out on a lot of the nuance that is the reality of vibration monitoring in soils. It's okay for initial analysis. When you're writing a geotech report, it's better to consider that than it is to not. And if you don't, have somebody, experienced with vibration monitoring on staff, it may be worth just using that simple approach to get some assessment. But it's really incomplete because you're not looking at adjacent structures. So, construction of them, if they're on pile, if they're, slab on grade, if there's any pre-existing conditions in those structures, which might exacerbate any soil movement conditions or might indicate that there already is soil movement under them. And it's also not looking at the vibration levels that are actually going to be occurring here. So if you're going to be pressing in pile, I know there's not a lot of press in pile here yet, but it's everywhere in Europe right now. So hopefully it comes here a little bit more. But if you're going to be pressing in pile, obviously you're not going to have as much vibration. You don't need to worry about 45-degree angle with the water table. The really important thing here that I want to get across, though, is that once the retention system is designed, it's really hard to change that, and it's really hard to convince somebody to change that based on something that might happen with vibrations. And this is not an exact science. There's a lot of kind of nuance and assumptions that we're making with this vibrations data. And at the end of the day, it's a prediction before damage happens. We're not monitoring vibration levels when it moves. We're trying to stop that from happening. So once that retention system is designed, it's pretty much fixed, and you could have some more issues by letting that move forward. So the second approach here is ground vibrations from pile and sheet pile driving, part 2, building damage, by Massarch and Felenius. I'm calling it the M&F paper going forward, so I'm not going to repeat all that. But this is basically a research paper where they did a big literature review of the vibration information out there, a bunch of different standards, and came up with a calculation-based approach, a little bit more involved for measuring your cone of settlement. So what you see here is you have a pile inserted into the ground. Is there a laser pointer on this? All right, pile in the ground. D is going to be your diameter of your pile. L is your insertion depth. And S max is going to be your settlement maximum, which is going to be right at the pile. So basically just a few variables that you need here to be able to get kind of a rough assumption of the settlement radius. So we can compare kind of the results of the DIN with no water table, the DIN with a water table, and the M&F paper. And we can see that, you know, the results are in line. So it's somewhere kind of in between, assuming, you know, with some basic assumptions of what our pile depth is. I did do kind of the water table was near the pile tip for these, so that's going to be kind of a maximum distance there. But, you know, these results are kind of in the same ballpark, so that's a good reference that, you know, the DIN method actually is fairly appropriate. You may under or over compensate a little bit there, but all of these results are kind of the same. What's nice, though, about the M&F paper is they include some additional calculations here that are really beneficial to vibration monitoring. So they have a max settlement calculation, which uses a soil compression factor, which is based on how high or how powerful your vibrations are going to be, just low, medium, or high, basically, and the density of the soil. So using this table, you can calculate your maximum settlement or approximate maximum settlement, and then moving forward with that, you can calculate settlement at the distance of your footing. So if you are working and, you know, your cone of settlement is 15 feet out, but your closest foundation is at 10 feet, you can actually calculate what the settlement could be underneath that foundation at 10 feet. And that's a really useful thing to get across when you're trying to have that conversation with, you know, your excavator operator, saying, you know, if you move forward with this, you could cause 2 inches of settlement under this building. That's a lot more than saying you may have settlement out to 15 feet. Pretty simple math here, pretty easy to bust out those calculations. So, you know, eventually, I kind of touched on this already, but you're going to get pressed by a lot of people to say, you know, what can I get away with on these projects? You know, we already have this foundation system designed. You're coming in the day before we start construction with vibration monitors and saying that we're going to settle the adjacent building. What can we do to give this a try and see? And that means you have to assign a vibration threshold to this soil. So if you decide that they're going to move forward and take that risk, then you need to have at least some assumption of a vibration threshold. And neither of those approaches really satisfy that need. So using the M&F paper, they provide this nice chart here that shows our shear wave velocity of the soil versus peak particle velocity and the risk of no risk, low risk, high risk. So this is really great because it says, you know, okay, you know, if we want to have a low risk project, we need to stay, and we have shear wave speeds of you know, 500 meters per second. You can assign kind of a risk level of where settlement is. The trouble is we never have shear wave speeds, right? Fortunately, the Department of Defense has created this nice table, and unfortunately the dot is covering some important information. So, but they have created this nice table that correlates shear waves with blow counts. So with use of this, you can then create a table showing what your blow count is of your non-cohesive soils with a risk factor and a vibration threshold. And at 3 different levels as well. So this is a really useful tool. You know, you have a number of different vibration levels here, and in my experience with, you know, working on several hundred projects and seeing vibration damage on, you know, a number of buildings as a result of soil settlement, I say these results are quite accurate. It's a little bit of, you know, jumping between multiple papers, which is an unfortunate thing to have to be doing, but it's also sort of, you know, where the industry is at right now with vibration monitoring. So something that Omnidots does to kind of help with this process is we allow different levels of alerting on our vibration monitors. So we actually have 3 alert thresholds. That way you can have an early warning threshold before damage, kind of say, hey, we're approaching threshold, we need to examine what the operations are and if we're going to keep increasing in vibration level. Then you can have a soil settlement threshold where you can say, hey, this is our soil warning. And then if they decide that, you know, they're going to continue to exceed that, you can have a 3rd damage threshold programmed in, which would be your actual damage to the structure threshold from the structure itself vibrating. So we allow different vibration levels. A lot of our competition does either 1 or 2 has a limitation. And we also have this cool feature where with text message alerting, you can put in a custom message. So your client isn't getting a message that says 0.1. They're getting a message that says approaching threshold, contact Ren, and you can direct them to actually just have that conversation rather than not know what's going on and just keep moving forward. And that message can change for each of the different alerts too. So I'm blasting through this. So I'll go through a little bit of lessons learned here. This is kind of some of the information that in my experiences. I didn't want to talk about specific projects because I'm not actively working on projects now and didn't want to step on anybody's toes. So a lot of these pictures are things I've pulled from, you know, various internet sources and are representative of the things I'm talking about, rather so than actual images from projects I worked on. One of the first steps and important lessons here is in placing the vibration monitors. So the monitor placement is very much dependent on the vibration threshold you're using and what you're trying to monitor. Many of the thresholds out there specify where they want to place the monitor. So I mentioned the US Bureau of Mines earlier. That's a very common one to see in the US. That very specifically says undisturbed soil as close to the foundation as possible. When you get into something like the German DIN standards, they have different thresholds for different placements. So if you're placing it on the foundation slab, you have a different one. They actually have one where if you place it on the top level of the building, that way you're monitoring whole structure movements. And it's a simplified version. So kind of different things, but you know, really here we're talking about soils, and if you're monitoring soils, your monitor should be in the dirt. So some things to keep an eye out for in sort of the running up to the project phase. Definitely look for pre-existing damage. So there's going to be small things. There's always going to be small things. But there are some signs in structures of soil settlement, of surfaces surrounding structures that, you know, if you're outside and scouting a site and, you know, making soil assessments at you know, maybe with test pits or something like that, it's worth walking around and just looking at the adjacent buildings and see if they have a big crack like this. Because if a building is cracking like that before work starts, it's already significantly settling. And once you induce vibrations in there, that thing is going to move fast, and it's going to move significantly. That's kind of that compromise. On the chart I showed earlier with vibration thresholds, anything where there's pre-existing damage like this, you're considering that a poor soil, and you're looking at a very low vibration tolerance for that building. I've seen movements as low as 0.08, which is in that level below, sensitive historic buildings and museums, where the soils are so poor and the building's so poorly supported that it's basically teetering, and as soon as that vibration hits, it starts to move. One of the important things related to this is, even if your site-specific soils are okay, if there's fills present and you have bad drainage on the neighboring buildings, that can cause, an underlying problem where that building is over a void essentially. And again, once it hits with any vibration, it's going to start mobilizing. So pre-construction surveys are super important, but in reality, some of this assessment should be going on during the geotech phase. So when you start monitoring, if you have some concern for vibration damage, especially with soils, something to really keep an eye on is the soil, believe it or not. A lot of people want to jump to looking at the building and watching for cracks in the building, but often an early indicator is going to be that the soil itself is showing signs of settlement. You're going to see cracks kind of radiating, typically, in a circular arc pattern out from the pile. And often also what you'll see is the soils start to separate from the foundation of the adjacent building. And that indicates that you're reducing that passive pressure of the soil, and the soils underneath are mobilizing enough that the topsoils are moving, and then supported loads are going to be moving soon as well. So that's an early indicator. Cracks in pavement as well. If it's strong enough that you're cracking the street 10, 15 feet out, you've got something to be concerned about for sure. There's deeper movement there because the streets are all built on compacted fill. So you can also see control joints opening up as well in concrete slabs. That's a big one to look for. And these opening of pre-existing cracks and control joints and things, you're just going to see that the soil is gone and all the dirt and debris that is normally in those cracks is just gone, and it's just open. It's usually very apparent that it's a new crack versus an old one. But that can change also within a matter of 24 hours, especially around a job site where dirt's flying everywhere. So it is important to be out there kind of early and often and checking on these higher risk projects. Excavation complications. This is really where the damage happens. Soil settlement and the soil conditions that exist under a building, typically they've been there for a long time and they haven't moved. They built the street out front, they built another building nearby, the system didn't move. But when you add in a second complicating factor of starting to excavate and some of the soil under the lagging sloughs out. So all of a sudden you have this void that gets filled in with other soil and you end up with a void under the foundation. Especially with washout, that's a really big one. If there's a heavy rain event, you can wash out a ton of soil from behind that lagging, and all of a sudden you have a void situation again. Another thing there is retention creep. This is something the structural engineer should be calculating, but basically as you excavate your earth retention, those steel piles, they're going to start flexing, and they're going to flex in towards the construction site. And so all that soil behind it all of a sudden has voids. And that can be a complicating factor where when you induce vibration to that, it's going to start mobilizing everything. Yeah, I mentioned already, reduced passive pressure and voids. That's what we're really trying to avoid here. And these complications, I wanted to put a picture on this, but they're so specific, and a lot of them are tied up in lawsuits that like I couldn't really find the right thing to put here, because this is where damage happens, and you want to try to avoid these situations, and you know, excavating really close in addition to vibrating and having poor soils is a recipe for disaster. The next thing will be to, if they're planning on removing the piles at the end, you need to do this process all over again. Because, like I said, you know, you're not always going to know if there's sloughing. You're not, you know, there's not supposed to be sloughing. So when it does happen, and your excavator operator is, you know, maybe or maybe not going to notify the construction team about it, you need to have some consideration for that. You need to know, you know, if there was retention system creep and the soils moved a bit and they, you know, maybe or maybe not got backfilled with sand or something. If any new cracks or damage did show up, then you're looking at, you know, real concerns that when they pull the piles, this could cause significant additional damage. You know, here's an example of movement where, you know, we're seeing over an inch of movement, and this was installed after the initial movement, which was estimated at ½ an inch to an inch. So these soil movements can be really significant, of, you know, 2+ inches, and at that point you're looking at major structural repairs and lawsuits and millions of dollars in repairs and damages and things. So these are not to be taken lightly, and a lot of times, you know, in my experience, is the assessment wasn't made up until the day before construction started, when the vibration monitoring team got called in. So I think that the industry here is getting a lot better with this, but I also wanted to educate you all on that. My last thing for managing risk is document everything. Tie your notes to when you're in the field, to the data for a reliable timeline, like you can do with our system. Take pictures and take more pictures, because the pictures you take are going to be your timeline. They're going to be your field notes, and they're totally reliable because everybody can just look at them and everybody wants to look at them. So if you're on site with these, just take pictures through the day, and everything you see, everything you think you see, take a picture of it. You can't have enough. Some of my photo references here. And then, yeah, I guess that's kind of wrapping it up here. I did want to say we do have an MGS promotion with our monitors. So if you're interested in trying one out, we can do a 60-day return policy on that. So basically you buy it, try it for 60 days. If you're not happy, send it back. We also can offer a free accessory, and, you know, depending what you order determines what that would be. That can be carry cases, batteries, things like that. And our base remote monitoring system, so basically this unit with a AC power cable, that starts at $3,150. So pretty reasonable starting point for a remote monitoring system. Any questions?